Hey there students, on this video we're going to be going over tabular integration. So tabular integration is a shortcut method for the integration by parts. Integration by parts formula, um, the formula for integration by parts is basically the antiderivative of u dv equals uv minus the antiderivative of v du. Okay? So this is integration by parts formula, but we're going to be using tabular integration to integrate special types of problems. So when do we use tabular integration? So types of functions that are candidates for tabular integration, types of functions for tabular integration. The types of functions are as follows. Tabular integration. Alright, so the type of functions that you can use tabular integration for are the functions that when you take in the antiderivative of a polynomial, multiplied by an exponential function, dx, or if you are taking the antiderivative of a polynomial function times a trig function. Okay, so these are the ones that are easiest to use tabular integration for, because when you're doing tabular integration, when you're looking for du, you basically, if you do du repeated number of times, the polynomial function will eventually go to 0, right? And then it goes away. So that means that whatever product you have after that, the trig function will get cancelled out since you keep multiplying by 0. So the goal is always to eliminate the polynomial function by constantly differentiating, and then you'll be left with the multiple antiderivative of the exponential or trig function. Okay, so what are some examples? Let me give you some concrete examples of functions where you use tabular integration. So if you have something like this, antiderivative of x to the third sine x dx, for example, this is an ideal candidate for tabular integration. Or let's say the antiderivative of x to the third plus 3x times e to the x dx. This is another excellent example for tabular integration. Okay, so let's try out an example for tabular integration, and then hopefully that'll help you deepen your understanding. So example 1 that we're going to work out, example 1, we're going to try out the antiderivative. We're going to try and find the antiderivative of x to the third e to the x dx. Okay, so when you want to use tabular integration, what you do is you're going to make a table, as the name indicates, tabular integration. On your table, you're going to have two columns. Okay, one will be your u column, and then the other will be your dv column. So this is u column, and this is going to be the dv column. All right, so what's going to happen here is you're going to keep differentiating this, and then this one you're going to keep integrating. All right, so this will be the ones where you differentiate, and then this is the one where you integrate. All right, so which one do you want to pick for which will be your ideal u? So we have two functions here. Either this is the u, this could be the u, or this could be the u. The question is, which of them will eventually become 0 upon multiple differentiation? The polynomial function, right? The polynomial function is always your u, because every polynomial eventually terminates to 0 when you differentiate it a certain number of times, depending on what the degree is. So in this case, our u is going to be x to the third, and then our du is going to be e to the x. Okay, so what I'm going to do here is I'm going to differentiate each row repeatedly until I get until I get to 0. Alright, so what's the derivative of x to the third? The derivative of x to the third is 3x squared. What is the antiderivative of e to the x? It's just e to the x. Pretty easy. Keep going until this is 0, okay? Differentiate this again, 6x. And then you integrate this, e to the x. And then keep on going, differentiate this to 6. And then you integrate this, you have e to the x. Differentiate this again, you have 0. Integrate this, you have e to the x, okay? You notice how this one keeps repeating, it doesn't go away, the e to the x component keeps staying there, okay? That's why we put it here. How do we put it here? We keep differentiating, it won't go away, and it will be a problem. But the polynomial function eventually that ends in 0, alright? So now, what we're going to do is we're going to start to draw our diagonals, alright? So I'm going to start from this one. This goes down to that. Like that, you always go down, and then this comes down to this. And then this one comes down to that. And then this comes down to this right here. Alright, and then this is how you do your signs. The signs always start with positive, so you're going to have, first one is plus, always plus, and then all the signs alternate. So plus, minus, plus, minus. Okay, what these arrows basically means is that you're going to be multiplying this term by that term. That's going to be the uv, and then this term by that term, that's going to be the next uv. This one will be the next uv, that will be the next uv, and then the integral of v du for the next term is going to be 0, so it won't count. Alright, so in this case, this problem is now going to be the antiderivative of x to the third e to the x dx is going to be x to the third e to the x. Let me move this down a little bit so that I can have enough space. Move it down here. So it's going to be x to the third e to the x minus, multiply this and this, 3x squared e to the x plus, and multiply 6x and e to the x, 6x e to the x, and then minus 6e to the x, and then don't forget your plus c. Alright, so there goes your answer. You see how easy that was? You could do this in a snap, like in a fraction of a second. Just set up your tables, integrate, differentiate, 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 integrate, 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 and then just zero diagonals going down, plus, minus, put them all together, and there goes your final answer. Okay? Alright, this is a 3. Thanks so much for paying attention to this presentation. Please subscribe to my videos for future updates. If you have any particular videos you think might be helpful to you, feel free to request it. And then you can find a collection of my clips all at math.serve.com. So have a wonderful day.